Thank you very much for that very kind introduction. It's a pleasure and an honor to be here. Thank you all for coming. Let me see where I should start with this. So we have to dim the lights a little bit, I think, to see what's going on here. But the title of the talk is Who Discovered the Periodic Table? And I actually have no idea who discovered the periodic table. And I'm going to tell you why. And that's what's going to take up most of the rest of the time here. When you open a chemical textbook today, you will see a periodic table. You'll probably see it before then when you walk into a chemistry classroom. When you open up your textbook, there'll be a historical sidebar there, which will have a picture of someone who will be the discoverer of the periodic table. That person will have a long, grizzly beard. That person will almost always be Dmitry Ivanovich Mendeleev, who is a chemist who worked in St. Petersburg. But if you have an especially ecumenical textbook, or if you had a German textbook about a century ago, they might also include a guy with a beard named Julius Lothar Meyer. If you have a really interesting, historically sophisticated textbook, it might also include a guy named Gustav Hinrichs or John Newlands. All of these guys also have long beards. Mendeleev's periodic table was discovered or invented, depending on what term you want to use, in 1869 or 1871, depending how you figure. Meyer's was discovered in 1864, 1870, 1868, or 1871, again, depending on how you figure. And the reason why people make these assessments that X discovered the periodic table is because they kind of think of it like it's a rock. Like, you found this rock, and that's what it is. The periodic table, I've discovered it first. But that's not what the periodic table is. The periodic table is a complicated mixture of information. And if you know what the periodic table is, what its essence is, you look for the person who found it first, and then you've got it, the discoverer. I don't know what that essence is, so I don't know who found it first. But let me explain what I mean. This, obviously, is the periodic table of elements. I know that in many of you this instills bad memories from high school. It's really quite a lovely construction. So what this thing does is it has two basic axes. Running this direction, sort of left to right, are increasing atomic number from 1 to 100 and whatever, depending where we are on this table. This one's a little old. We have some more. Atomic number is the number of protons that are in the nucleus of an atom, which determines how many electrons are outside the atom, and therefore its chemical properties. None of that's true in the 19th century. No one knows about protons. The electron is discovered in 1897. Mendeleev doesn't believe in the electron. There's all sorts of reasons why the electron is not a good way of thinking about it. So in the 19th century, that's not how they order it. They order it by atomic weight, which is this number down here. You can do that for most of the way, and generally the atomic numbers increase as you move across and down. There's a couple of sticking points. Tellurium is actually heavier than iodine, and nickel and cobalt are wrong. But basically, they all increase that particular way. So why would you want to do this? Well, when you array them in order of atomic number, or generally increasing atomic weight, you find that you end up with vertical periodicities. That is, every so often the same properties recur. And that's extremely interesting, that all of these elements act similar, and they act similar with a kind of regularity. And therefore, you can read a huge amount of information off of this table. If you know something about manganese, you know something about technetium, which doesn't exist naturally in nature. But you know what its properties would be like because it's below it. It's an amazing condensation of information. There's lots of things about this that weren't true in the 19th century. These rare earths are really tricky, and they didn't really know many of these in the 1860s. And this thing was discovered in the 1890s, 1900s, the noble gases. They don't know about those either. But the basic idea is to have these two axes, where you do chemical properties, which is related to the bonding power of an element, or its valency, and you have atomic weight, or atomic number, on the other axis, and that way you get the properties and the weights correlated. Two-dimensional grid. It's extremely sophisticated. None of this stuff is true in the 19th century in terms of what it is. So that's what it is today. What was it? Or what is the essence of the periodic system? So let me tell you before I get to that what I'm going to do today. I'm going to talk about three different things. First, I'm going to provide an analysis using the periodic system as an example of how we should and should not think about priority disputes in the past. The history of science is littered with people claiming they discovered the same thing first. It's one of the many ways in which science is done. Two people come up with a discovery very close by. Whoever gets it first gets the credit. It's a very important feature of science. But there are some ways of thinking about this that are helpful and some ways that are not. And I'm going to use this as an example. Second, I'm going to talk about how the periodic system emerged for the case of Mendeleev and for Meyer. and in particular, the pedagogical context in which they came up with the system. That is, how they built it into their teaching, and how teaching, in fact, generated the tables that they used. I'm going to do that in order to point out that they're not talking about the same system. They have things that look identical to us, but they think they mean different things. And the third thing I'm going to do is provide a brief history of why that periodic table priority dispute happened and why it got so nasty so fast. And it did because of very local tensions between Germans and Russians in St. Petersburg. There's a very particular German-Russian conflict going on that's very, very local, with a set of maybe 15 people involved, that spirals into a big fight about who discovered this law of nature first. So I'm going to do those particular three things. Hopefully that's not too many things. So what is the periodic system of elements? Is it the abstract idea that there should be a system that organizes all knowledge, that this abstract idea should exist? Is it recognition that there's a periodic law or some kind of regularity that undergirds it? Is it putting them in a two-dimensional, some sort of tabular format, 2x2 format? If so, which one? There are about 100, a little less than 100 topologically distinct versions of the periodic system that you can look at. They're in 2 or 3 dimensions. So which one of those? This is the standard one, but it's in many respects not adequate. Depending on what you want to do with it. It's not good for spectroscopy and other things like that. Even if we just consider the issue of what the law is supposed to be, we find that historians, chemists, and philosophers have a lot of disagreement about what the periodic table's essence is, what the essence of the system is. Depending on which of these you pick, you find the person who did it first, and you find the discoverer. So possibility number 1 is recognition that, what I said earlier, that the periodic variation of properties that happens with rising atomic weight. Or you could say that recognition plus putting it in a 2-dimensional grid, or possibly a 3-dimensional grid of some kind. Classifying all of the known elements, not just some. In the 1830s and 40s, various people classified 3 elements and showed that there was a regularity with those. We don't consider them discoverers of the periodic system. So you have to do all the elements, not just a few. How about leaving gaps? In the 1860s, by the end of that decade, 63 elements were discovered. There are 92 naturally occurring elements. They obviously didn't know about a lot of them. So some people, when they made their periodic systems, left holes where they thought something should be, but was not discovered yet. They could use the periodic system to look at the pattern and try and correct some of the empirical values that you find. Like say, oh, that atomic weight's wrong. It should be this because the system requires that it be this. That's called retrodiction in philosopher language. Or you can predict properties of new elements. That is, look at those gaps and find something new in it and use it as a law of nature to predict something new. So these are all candidates. Different people have proposed each of these things as being an essence of the system. So depending on what you choose, you get an answer to the who question. So the first candidate is Alexandre-Émile Bégoyer de Chancourtois, who in the very early 1860s published in a French mining journal something he called the telluric screw, the vie tellurique, which you can see here. And he arrayed all the elements by increasing atomic weight and drew lines through them, and he noticed that there's a vertical periodicity in their properties. So if you believe that number 1 and number 2, you end up with him being first. And again, there's the beard thing going on. John Newlands, a Brit, is another possible candidate. He discovered what he called the law of octaves. He classified all the known elements, and he doesn't use atomic weight. He assumes we know what they all are already. And he lists them from 1 to n, and he puts them in order and notices that their properties repeat every 8th element. So he calls this the law of octaves based on music. And you get the families going along this way, which, is very impressive. William Odling, another British chemist, comes up with a system that looks very similar, and he's closer to number 3 in that he classifies all the known elements, and also he has a little bit of number 4, he leaves some gaps where he thinks things should be. Gustavus Hinrichs is the Dane who moves to the Midwest and comes up with the first spiral system, and then Lothar Meyer, who does 4 and 5, and then finally Mendeleev. So depending on which of these things you think is most important, you give credit to one person. We now universally seem to believe that predicting new elements was the crucial feature of the periodic system, so this guy gets the credit. That's a decision we've made now. That was not obvious to people then. So I want to give you a brief history of how people have thought about these systems in the past and how we've come to give Mendeleev the credit. And there's an interesting sub-story, a philosophically interesting sub-story beneath that. So I'm not going to sit here and sort of say who's right and who's wrong. I told you in the beginning I don't know, and I wasn't kidding. But this is an interesting parlor game to sort of guess who's first, who did it right, what the periodic system is, but it's not very good history. And so we're going to do some slightly better history tonight, hopefully, and maybe make you like the periodic table a little bit more. So this issue, something odd happened in the 1860s, right? A whole bunch of periodic tables happened all through the 1860s. There are none before, and there are none after. Well, at the end of the decade, you have a table, so there's no reason to have more. But why were there so many in the 1860s? The 1860s is an incredibly interesting time, and there's a reason why all this independent discovery happens roughly around this period. So the fact that it's independent is in itself a little tricky issue because some of these people knew about other of these people when they published their systems. So they're not all totally independent of each other, but most of them didn't really know about someone else's system until they'd already started to work on theirs. So what happened in the 1860s? Well, in the 1860s, in both inorganic and organic chemistry, just about every concept, every notion, every theory was up for grabs. Everything was being revised. And that's because a lot of interesting innovations had happened in organic chemistry and interesting innovations had happened in physical chemistry, such as spectroscopy, being able to identify elements by their spectral lines. So huge amounts of new information happened. In 1860, in September, in Karlsruhe, which is a small town in the south of Germany, then south of the German states. Germany is not a country yet. There's a congress organized by an organic chemist named August Kekulé to try and standardize some of the concepts in chemistry, because it's all too confusing. We have 18 different formulas for vinegar. No one can agree on anything. We need to standardize this stuff because we can't teach properly if no one can agree with everybody else. So he gathers call out internationally for chemists. It's one of the first international conferences in a science. It's not the very first, but it's one of the first. And at this conference, the star speech is given by this man, Stanislao Canizzaro, an Italian chemist who later becomes a senator when the Italian state unifies. And Canizzaro gives this speech saying we should revive his countryman Amedeo Avogadro's 1811 theory about how to calculate atomic weights. And if we do that and rigorously and vigorously apply it to everything, we can standardize all the atomic weights so that everybody uses the same system. That would involve changing some things. So the atomic weight of carbon, most people thought at the time, was 6. If you apply Avogadro, it's 12. Oxygen goes from 8 to 16, and some of the ones get cut in half. So you get all these new atomic weights. When you have all the atomic weights on the same scale, it becomes very easy to order them in order and see the pattern. So you need to have this particular speech and this particular standardization to happen before any of the reform can happen, before you can have any periodic system. But as soon as this speech happens, people start making periodic systems all across Europe. Two people in particular, two young postdocs who were in Karlsruhe to listen to this conference, later cited as incredibly important in their development. Their names are Dmitri Mendeleev and Lothar Meyer. Both of them are there, they don't meet each other, but they both hear this speech, and it triggers them on a path to find a periodic system. There's another reason why they can discover, why the periodic system happens in the 1860s and not earlier and not later. There are very few rare earth elements, that island on the bottom of the table. Those have very similar properties. So you don't see a periodicity with those the same way you see a periodicity with the basic elements and the transition elements. So when there are very few of those, it's easy to see the pattern in the system. But if you tried to incorporate each of those, the system would look strange. And people spend a lot of the 1870s and 80s trying to figure out what to do with these elements. They thought, Mendeleev thought it was the iceberg of the system, the thing that was going to sink the system. So in the 1860s, there's this unique moment when you have a lot of new information, it's all standardized, but you don't have too much information, which is very important. So you get 6 periodic systems within this decade, none earlier, and had they waited longer, probably none later. So what does this have to do with pedagogy? And this is sort of part 2 of the talk. I'm going to look at 2 particular textbooks written by these 2 guys. Here's Dmitri Mendeleev. His textbook is called The Principles of Chemistry, which comes out in Russian, the first edition, from 1869 to 1871. It has 2 very big volumes. I'll talk about that in a minute. And then Julius Lothar Meyer comes out with a book called The Modern Theories of Chemistry in German that comes out in many editions. The first is 1864. Both of these books go through many editions. They expand grossly in size over time, and they become totems of their own kind. I'm going to focus on the periodic system and how it emerged in each of these textbooks to change the question a bit. Not who discovered what, but what did they want to do with it? What did they want to do with the periodic system? What did they think it was for? And that is something you can see. And what it was for teaching students. The question is, what do you want to teach the students? And that's different depending on who you talk to. And that will give us a clue to one of the big mysteries in the periodic system, which is, why does this guy not predict any elements? He has the system, he has the gaps, he fixes old elements, but he doesn't predict new ones. And the usual answer is, to put it bluntly, that he's chicken. That he's not bold, and this guy's bold. And he's bolder than this guy, and this guy just doesn't do it. That's not right. There's plenty, and I'll explain why I think that's not right. And this often gets tied in with a lot of nationalist stereotypes about Germans being cautious and Russians being reckless. All of that stuff's not true. Sorry if you thought it was true, it's not. So let's start by talking about pedagogy for a bit. And first, let's talk about Mendeleev's pedagogy, both where he learned and where he taught. He's actually very confined in place. He doesn't go a lot of places. Mendeleev was born in 1834 in Siberia, a town called Tobolsk. When he is college age, his mother takes him to Moscow to try and enroll him at Moscow University. It's the oldest university in Russia. He's not let in. So then they go up to St. Petersburg and try and enroll him in the university there. He's not let in there either. So he gets into his father's alma mater. I'm not going to say anything in this particular context about getting in legacies, but he went to his father's alma mater, which is the Chief Pedagogical Institute, which is located on the campus of St. Petersburg University and has many of the same faculty members who teach in both places. But it's designed to train teachers. Mendeleev is trained to be a chemistry teacher. He does very, very well, and he ends up getting the equivalent of, he gets a candidate degree, which is somewhere in between a doctorate. And it's around a doctorate. It's a little bit different than that. But he gets that at St. Petersburg University at the Chief Pedagogical Institute. And then his advisor sends him off on a postdoctoral trip for 2 years, from 1859 to 1861, to Heidelberg, Germany. And he goes to Heidelberg for a bunch of reasons. There's a lot of chemistry happening there in that period of time. The chief chemist there is Robert Wilhelm Bunsen, but Hermann von Helmholtz and Gustav Kirchhoff both are there. It's a very exciting place in the physical sciences. Mendeleev doesn't study with any of those guys. He spends his time in his apartment. He makes a lab there and does interesting work on organic chemistry, and he hangs out with one untenured professor of chemistry, who I'll talk about in a little bit. But mostly he hangs around with Russians and that one German guy. But he learns a lot of chemistry, and then he comes back, and after adjuncting for a while, and while he's there, Heidelberg is conveniently close to Karlsruhe, so he ends up going to Karlsruhe, hearing the Congress. He comes back to St. Petersburg in 1861 in February, 2 weeks before the serfs are emancipated. Then he adjuncts for a little bit, and gets a job in 1864 at the St. Petersburg Technological Institute, training engineers. He does that job for 3 years, and then he succeeds his mentor at St. Petersburg University in 1867, where his job is to teach general chemistry. And so what he is supposed to do is teach that big intro class, which is required for anybody in the natural sciences faculty. And now he's got a problem, because he has to give them a textbook so that they can learn the chemistry that he has to give. But the problem is that in the 1860s, all these transformations have happened in chemistry, and he doesn't have a Russian book he can assign. So there are two basic options. The first is to find an English or French or German textbook that's up to date and translate it. He'd done that before for some other teaching jobs earlier. But he can't really do that, because by the time he gets it translated, it'll be out of date, because the transformations are so rapid. So he decides to write one of his own. And that's where the idea for the principles of chemistry comes. It's also more lucrative to have one of your own, because you can assign your textbook to your students and you get royalties. And he thinks about that very seriously. It becomes part of a divorce settlement later, but I'm not going to talk about that. So he wants to write a book, The Principles of Chemistry, and he's got a contract. And it's a fantastic book. You probably have it here. It's got 2 volumes. The first volume is designed to teach you the basic principles of how to think like a chemist. That is, how do you find oxygen? How do you purify it in nature? What is it good for? What do you use it in? Where, like, etc. Like, which kinds of minerals have lots of oxygen content, and so on. And so what he does is go over 600 pages as volume 1 and 600 pages as volume 2. In volume 1, he goes lovingly over the 4 organogens: hydrogen, oxygen, nitrogen, and carbon. And then in the last couple chapters, he deals with the 4 halogens, which is a known family of fluorine, chlorine, bromine, and iodine. And that's a family that everybody knows reacts the same way. So he deals with 8 elements in volume 1. And he's very happy with it, and he sends it off in late 1868 to the press so they can print it. But now he's got to write volume 2, which has to be the same length. And he's got 55 elements to put in the book. And I don't envy him on this particular position. So he has to figure out what to do. So the first thing he does is put the alkali metals, that column which has sodium and potassium in it, because he knows those things, everybody knows they're a family too. So he deals with them. And then he juxtaposes them together in around February 1869, exactly when is tricky, and notices that the increase in atomic weight between, say, sodium and potassium is similar to the increase of atomic weight between chlorine and iodine. And then he's like, oh, look at that. It's almost the same increase of atomic weight. These things are increasing at the same amount. Maybe there's a pattern here. And he has this brainstorm and realizes that he can put other elements in groupings and find these similar patterns. And he starts thinking about writing the book not in terms of individual elements in loving detail, but families, and that way compressing the book. So that's the idea. And he takes this idea and he produces this in February 1869. This is Mendeleev's first periodic system. He calls it a system. It's not a table. He never uses the word table. It's like our modern table if you turn it clockwise 90 degrees and reflect it in a mirror. Instead of the weights increasing this way, they go down. And you can see that the families are here. Here are the halogens: fluorine, chlorine, bromine, iodine, sodium, potassium, and so on. You can see that he puts these are the opposite ends of the table now, the fluorine column and the sodium column. And if you cut the table there and rip it apart, you get our modern day table. But he doesn't do that because he started by comparing these two, and he builds the table out. So you can see that the original table bears the signs of its use in a textbook. That's where he made it. There's a couple of things, there's many things that are fascinating about this system. I'm going to only point out 3 of them. The first is that it's not done. There's all these things over here that are not in the right order. He doesn't know where to put them, so he just kind of threw them on the end and said, I'll deal with those later. The second is that he has mistakes in it. So uranium is right here with atomic weight 116. If you guys go to the nuclear talk very soon, you'll learn that uranium has an atomic weight of 238. So it's about half. So it hadn't been fixed yet. Later on, Mendeleev fixes it. He doubles it because he's like, that's not right. 116 can't be right. And the third thing is that there are these question marks here at 45, here at 68, and here at 70. These are elements that he thinks are gaps, but he doesn't just say gap. He says a gap, and he predicts their atomic weight. So the predictions are here from the very beginning. It's extremely interesting. By 1871, he finishes the book and sends it to the publisher, and this is what the system looks like. It's very much like our current system. And it has an overleaf. This goes out of the book, so you can have it outside while you read the book, so you have a periodic system that you can use while you read. It's designed, again, for a textbook. So it's an extremely pedagogically oriented table. Mendeleev also always stressed that it was for teaching. So repeatedly, he talks about it in many instances. So here's an example. Quote, I will add still another remark. It is that the use of the periodic law facilitates the learning of chemical facts by beginners, which is what we still use it for. I have come to this conclusion during the courses of lectures that I have given for 2 years and during the preparation of my Traité de chimie inorganique, he says it in French, now published in Russian, which treatise is based on the periodic law. That's written in English, that article. So Mendeleev was a very flighty and very difficult person and a very cantankerous colleague, but he was extremely dedicated to undergraduate teaching, and that's what he thought this was for. But the fact that it's for teaching and embedded in a textbook highlights also some features of Mendeleev's conservatism pedagogically. He likes the table because the table doesn't require you to make any hypotheses. This sounds a lot like Newton. He writes a letter to Emil Meyer, the German chemist, in 1871. I want only that you will pay attention to the fact that I do not set up any hypotheses, because in my view, these often seduce students as false keys, and thus tends to slow down the development of science. That's extremely interesting, because Mendeleev is basically hostile to most chemical theories. He's skeptical towards atomism and valency, which we think the periodic system now is about correlating atomism and valency, and Mendeleev thinks both are dodgy. He doesn't like the idea that atoms have substructure, that they might have something like protons and neutrons that make them up. That's called Prout's hypothesis in the 19th century. He thinks it's wrong. He doesn't believe in the electron when it's discovered in 1897. He doubts the existence of noble gases when they're first discovered in 1894. Eventually, he accepts those. And he doesn't believe in radioactivity, even though he visits the Curie's labs. Generally, Mendeleev is consistently hostile to chemical speculation, which is extremely interesting, and it's pedagogical in orientation. He doesn't like theorizing in front of students because students like the theories too much. They don't have the right skepticism towards it. And the table's perfect for this, right? Because the table doesn't have any explicit theory in it. It's just an ordering of elements by atomic weight. And they can use it to think chemically without getting seduced by hypotheses. There's one exception to Mendeleev's pedagogical conservatism. It's kind of a big exception. But notice that Mendeleev, in all of these things, he's on the wrong side, right? Like every time he makes a decision, he's wrong. That's interesting because we've forgotten all about this because the one exception is so important. And that is that Mendeleev predicts elements. And he's right 3 times, stunningly. He never thought it would happen this fast. But in 1871, he publishes the system with the full predictions. Very detailed, what kind of crystalline structure they'll have, what the density of the elements are going to be, their specific heats, their weights, their valency, or their combining power, which is what he uses, their oxidation level. In 1875, Lecoq de Boisbaudran discovers gallium. In 1879, another element is discovered called scandium. This is discovered in France, scandium is discovered in Sweden, Norway, and germanium is discovered, you can guess, in 1886. This nationalism is a theme that runs through the rest of what I want to say today. So this is an extremely theoretically bold thing to do. I mean, he is kind of bold in doing this, but he's not theoretically bold in almost any other context. And he doesn't do this in the textbook. He does this in articles. It's not for students. This is what you can do to chemists, but students be very, very conservative with. He also has a theory of credit that he embeds in his explication. I don't want to get into this very much, but he has a vision that you should give credit. Lavoisier gets credit for oxygen because Lavoisier discovered it or explained it in the most comprehensive way, even though Priestley found the substance first. So, likewise, if other people found a table first but didn't predict, they didn't fully understand the system. And so he should get credit for it. He uses history for that purpose too. So, and therefore, if it's full credit that's really the issue that's extremely important, then we know who should get credit for the periodic system, the person who makes predictions, which is the furthest implication you possibly can have. And we know who that is. It's not Lothar Meyer. Lothar Meyer didn't do that. So let's talk about Lothar Meyer's particular pedagogical origins. It's very different from Mendeleev. Mendeleev was Petersburg, a little bit of Germany, and then Petersburg for the rest of his life. Meyer is very characteristic of German chemists in that he went everywhere and learned different kinds of chemistry from different people where he went. It's very common in 19th century Germany. Academic freedom means you can go from place to place to place and study a semester here, a year there, a semester here, take courses with different people. And he learns different kinds of chemistry, physiological chemistry, physical chemistry. He learns spectroscopy, he learns organic chemistry. So he moves around. He starts in Zurich. He's a little older than Mendeleev, but he was sickly as a child, so he was held back. So they're almost exact contemporaries. At Zurich, he works with a guy named Ludwig. At Würzburg, with Virchow, who's a very important man in cell theory. At Heidelberg, he goes there, not overlapping with Mendeleev, really, where he works with Bunsen. Then he goes to Königsberg and learns some physics. And while he's in Heidelberg, he also he's nearby, and he goes to the Karlsruhe Congress. So it's very itinerant. Likewise, his pedagogical jobs are very itinerant. He starts out in Breslau in 1859, which was the oldest university in Prussia. I believe it's the oldest one in Prussia. Now it's in Poland, called Wrocław. But he's there for a few years. Then he goes to a forestry school at Neustadt-Eberswalde. Then he goes to a polytechnic school in Karlsruhe, teaching engineers, similar to Mendeleev. And in 1876, he ends up at Tübingen, a major research university where he stays the rest of his life. So he's very itinerant in this particular process. And that's interesting because he's learned, first of all, he's learned lots of different kinds of chemistry. And then he has to teach lots of different kinds of students. And so he's actually very attracted to chemical theory like atomism and valency because it's useful to teach different kinds of students the basic principles of how to think chemically. And so he's extremely excited by atomism and valency. So in 1864, he publishes the first edition of Modern Theories of Chemistry. It's 137 pages long. It's not a very big book. It's very much unlike Mendeleev's. The whole point of this book is to juxtapose atomism as one theory and structure theory and organic chemistry to illustrate valency as another theory. So he has part 1 and part 2, and then they fuse together at the end when he produces this thing, which is a periodic table. Here it's these are valencies, 4, 3, 2, 1, 1, 2. And here you have carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. You have all these. And he marks the differences in atomic weights between the levels. And he notices that it's about 16 to 17 here, between these two levels. Here it's 44 to 46. So he's doing the same thing Mendeleev did in 1864. He doesn't have a full table, but this is the basic idea. And he's extremely excited about this particular system because it unifies the two theories he thinks are interesting, and he thinks students should learn about them. It's half a textbook and half a polemic with other chemists to say, don't dismiss theory, it's really important. And in 1872, in the second edition, he produces this. And that's a periodic table, right? Like that just looks like our periodic tables in the way we would have them now. He also, in 1870, publishes an article, and this is what he's famous for, where Mendeleev never did this, which is atomic volumes, and he has a curve of their atomic volumes, and the shape of this curve is periodic. It has a structure that's very periodic in it. So after Meyer does this theoretical thing, you think he's going to predict elements, right? Because he's incredibly bold and very theoretically sophisticated. But he doesn't. This is what he says right after publishing it, printing the table, the first table. It is surely not to be doubted that a definite regularity prevails in the numerical values of atomic weights. It is rather improbable that it is as simple as it appears if one leaves aside the relatively small deviations in the values of the evident differences. In part, indeed, these deviations can be part of experimental error. But this can hardly be the case for all of them, and entirely certainly one is not justified, as is seen all too often, due to a suspected regularity to want to arbitrarily correct and change the empirically determined atomic weights, before experiment has set a more exact determined value in its place. This says, don't predict anything based on this. I know I have two really good theories, but experiment's incredibly important. Don't get carried away. Don't speculate. So after defending theory for so long, he wants to not scare off his colleagues and say, look, don't go too far. It's important to be a little conservative in predicting because we don't know how certain our theories are. Atomism, very certain theory. This table, not a very certain theory. So don't rely too much on it. And that's interesting because Meyer is pedagogically incredibly radical. In Modern Theories, 1864, he endorses atomism, valency, the idea that atoms have substructure, structure theory, all things Mendeleev doesn't believe in. And he's right on all of them. On every issue which he predicted, where he stated, I believe this theory, we agree with him. And with Mendeleev, we disagree. The interesting thing is that prediction point. It's a sticking there. It's very difficult to deal with because he doesn't predict anything. So why is that? Well, we have a paradox here. Mendeleev is incredibly conservative about theory, yet he'll predict. He thinks that's okay. Yet Meyer is incredibly radical on theory. He's at the cutting edge, but he excludes prediction. He says that's not okay. So why is that? Well, I think there's two reasons for that. The first is the border between chemistry and physics. Meyer is very careful in the book to say these are chemical theories, atomism and valency. They're not like the theories in physics. They're not like Newton's laws. And as a result, physicists predict. That's what they do with their theories. We explain with our theories. We do something different. And so he's very interested in setting up a boundary between chemical theories and physical theories. Mendeleev always flirted with physics. He was always incredibly interested in it, and he's trying to erode that distinction between the two disciplines. And so the prediction is part of him saying, I'm like a physicist. I can do the kind of thing you do. So there's a deep difference in what they think chemistry is for, and you can see that in how they treat their table. And the second is about the pedagogic goals they have. Mendeleev's goal, remember, is to teach chemists how to think like a chemist, teach young students how to think like a chemist. And to do that, you don't want to seduce them with theory. In chemistry articles, in journals, you can predict all you want because responsible people will read those. But you don't expose students to that stuff. Meyer is the opposite. Meyer thinks you should teach students a proper respect for theory. And part of a proper respect for theory is not going overboard. So you can see the pedagogic origin in the table itself. So that's what I wanted to say on part two. I just think we shouldn't, be a little too harsh on Meyer. Meyer has a whole project here behind not predicting, and it's part of what it means to be a responsible teacher. Okay, the third part of the talk is what I'm going to start now, and I want to talk about why this happened, why there's a fight between Meyer and Mendeleev. Right now I've made it sound like they have different views, but as if they don't talk to each other. They talk, they write against each other, they scream. It's extremely vigorous, angry fight. So why did this happen? Well, it happened because of one word. So it happened with one word because of this man. This man is Friedrich Konrad Beilstein. He's born in 1838 in St. Petersburg of a German family that lives there. He's fully bilingual, Russian-German, and gets educated for graduate work in Germany, and he stays in Germany for a while. but he's still very tied to the Russian chemists. He eventually goes back to Russia in 1866 and takes up Mendeleev's old post at the Technological Institute. He's the editor of so he's in St. Petersburg in the late 1860s. He's also one of the editors of the Zeitschrift für Chemie und Pharmazie, the Journal of Chemistry and Pharmacy, which is a German chemical journal. It's not the major one. It's a small one, but it's one that people do read. And he's very eager to get Russians to publish in it. So he tells Russians all the time, please give me your articles. I'll have them translated. We'll publish them in German. That way people will read you, because no one can read you in Russian. No one knows Russian. So no one who matters knows Russian, so they'll read German. And that's true in this period. And for a variety of reasons, Russians like to publish in this journal. They like to publish in it even before Beilstein. I'll get back to that in a minute. So Beilstein's really busy, as is his wont, and so he has to do a bunch of different kinds of things. So he does what most chemists in his position would do, is he gives it to a grad student to translate, a guy named Fersman. And Fersman is translating it really quickly, and he makes a slight mistake in the translation. So Mendeleev says, when the atomic weights increase, there's a periodicity in their properties. They change periodически, periodically, and period is in there, so it's really periodic, based on math. That's the analogy. And instead of translating it as periodisch, Fersman translated it as stufenweise, which means stepwise or gradual. So Meyer reads that in this 1869 abstract in the Zeitschrift für Chemie und Pharmazie, which says there's a longer article in Russian, but this is an abstract of it. Meyer reads it and says, oh, well, Mendeleev is so close. He knows that there's a change, and the table's very good, but it's not gradual or stepwise, it's periodic. So he writes an article saying, Mendeleev is almost there, it's periodic. And so he goes one step further. Mendeleev is kind of incensed. He's like, what do you mean? I said periodic. And Meyer says, well, you know, but I read the thing, and it says here's gradual. And he says, well, you should have checked the original. You knew it was an abstract of something else. And Meyer says, well, there are several priority disputes that start after that. The first one, which is in 1871, is very, very hostile. It takes place entirely in German. And it's basically Meyer saying, I don't have to learn Russian. Come on, it's ridiculous. I have to read German, French, English, Italian, and Swedish. Enough. If we had to learn Slavic, no one's going to do anything. We're just going to spend all our time reading languages. It's awful. This obviously doesn't play well in St. Petersburg as a strategy. So there's a very nasty dispute that happens this way. And Beilstein, because he's responsible for the translation, he doesn't sell out the grad student. He takes responsibility. And they never trusted Beilstein anyway because he's German. They think he's German. So it gets very nationalist very quickly. And then it dies down by 1873-4. And then in 1880, Adolf Wurtz just can't leave it alone. Adolf Wurtz is at the Sorbonne in Paris. He's an Alsatian chemist. He's bilingual French-German. And he earned the ire of the Germans in 1868 by publishing in the Dictionary of Pure and Applied Chemistry the opening line, chemistry is a French science, grounded by Lavoisier. The Germans find that not very funny. So there's a big fight that happens in the late 1860s, again, about who is more chemical. And then in 1880, Wurtz writes a letter to the Berichte of the German Chemical Society, the leading chemistry journal, and says, you guys keep saying that Meyer discovered the periodic system, but he didn't. Mendeleev did. He did it first. And that gets everybody really mad again, because the Germans are mad at this like French guy tweaking them again and trying to steal their credit. The Russians get involved again, and it's very bad. And so then in 1882, the Brits try to step in and solve it. And they do temporarily solve it by awarding the Davy Medal to both of them. So here's the Davy Medal, and the Royal Society gives them to Dmitry Ivanovich Mendeleev and Lothar Meyer. And this is great, right, because it's alphabetical, but Mendeleev is first. So it does everything. So this works for a while. By the 1890s, after the predictions are all discovered, everybody changed their minds about what the table was about. And they think it's about prediction, so then they give all the credit to Mendeleev. But in the 1880s, that's not obvious yet. So everybody thinks it's about something else, and they think they both deserve some kinds of credit. So why did this happen? Like, it's like a huge mess. Why did this take place? Well, I'm going to rephrase the question. This happened because Mendeleev published in the Zeitschrift für Chemie und Pharmazie. He published in that German journal a translation of a Russian article. Why did he do that? He didn't just do it because Beilstein asked him to, right? Like, because he could have published in other contexts. He published in that journal specifically because of something that goes way back to Heidelberg. Remember, I mentioned that Mendeleev went to Heidelberg in 1859 to 61. Very many Russian academics, postdocs, were sent abroad in this period. A lot of the physicians end up going to Vienna, a lot of the law people end up going to Bonn or to Berlin, and the chemists predominantly end up going to Heidelberg. And so there's a little colony of them there, and he goes there. But while he's there, he goes to the Karlsruhe Congress, but mostly he hangs out with Russians. And I said one German. That one German is Emil Erlenmeyer. Emil Erlenmeyer is incredibly interesting. He's a very theoretically flashy man, and he's the editor of the Zeitschrift für Chemie und Pharmazie. He's the editor of this particular journal. And the Russians like him. He's the only German they don't think is snooty. They have a nickname for him, Jeremich, which he is a term of endearment. They correspond with him in German, and they really quite like this man. The Germans don't like Erlenmeyer, because in Erlenmeyer's journal, he publishes their articles, and then he writes, puts footnotes in, or even embeds in the texts sarcastic remarks, question marks, and so on. And he does that even when they didn't publish with him. He translates an article from French, puts it in the journal, and makes fun of it. And this means that no one in Germany reads the Zeitschrift. They don't like it. Its sales go down. The only people who still read it are Russians, because they like him, and they didn't know that that was weird. So because of their friendship with this guy, this is not because the Russians are crazy or dumb or something. It's just they know this guy, he's very nice to them, and they think this is a perfectly fine way of being a chemist, because that's what they're learning from him. And then in 1865, no one's reading the article, the Zeitschrift, so it goes to Göttingen. It moves away from Heidelberg. And then it goes to Beilstein and two friends. And then Beilstein goes back to St. Petersburg. And so the Russian connection continues throughout this period. And because of that Russian relationship with this particular journal, Mendeleev is predisposed to publishing in German in this particular weird context, which is why he ends up in that journal with that particular translator at that particular time. So it's a bunch of very small local relationships between lots and lots of different scientists, well, not lots, very few different scientists, both in Germany and in St. Petersburg, that produces a periodic table fight about nationalism. It's not because the Russians hate the Germans, it's because Mendeleev doesn't like Beilstein very much, but he likes Erlenmeyer, and Erlenmeyer has this other relationship with Wurtz. It's this very intricate narrative story that we now flatten out and say Mendeleev discovered the system first, Meyer didn't. And interestingly, even though Mendeleev really wanted to have credit for the periodic system, that's not the only thing he wanted. He was 35 when he did it, and he thought he was going to do much better things later. So he wanted always to be something more than just the guy with the periodic system. But that's not what happened. Everybody forgets the stuff he did later. This is a statue of him in St. Petersburg. It's the only statue of him in St. Petersburg. And he's sitting looking on Moskovsky Prospect, which is the road that connects St. Petersburg and Moscow, looking at the St. Petersburg Technological Institute, his first job. And on the wall behind him, you can see there's a periodic table. He's sitting in front of the Bureau of Weights and Measures, where he had been director to introduce the metric system into Russia. No one remembers that. They just remember the system. So the whole priority dispute succeeded all too well. Anyway, thank you for your attention.
I'll have a microphone. We'll have two microphones for questions. And we're also going to turn up the house lights. Any questions? Okay. Let me come around this side.
In scientific writing today, is it 100% in English, or is there still leading edge research and writing in other languages?
Well, it depends on the science, but in general, it's about 97 to 98% English. So by 1980, it's 80% English, 14% Russian, everything else, the other languages. In 1880, so a century earlier, it was a third, a third, a third. And Russian wasn't on the board. French, English, German. Russian is like tiny. Now it's almost all in English. But that's not true in every field. Mathematics is not quite as Anglocentric. I don't know the exact figures, but it's below that number. And there's a lot of French and German stuff still produced. Much of it gets translated, but some of it doesn't. And in certain fields like astronomy, there's still Russian that matters. But even the Russian mathematicians, many of them now publish in English. There's been a tipping point, and that's where the transition happens. But the transition started to really take place in the 60s. That's when you start to see a real transition. But for a while, Russian was on the rise, Japanese was on the rise. It's a very complicated, intricate story. But it really does depend on the science. Chemistry was overwhelmingly German in 1900. and now is overwhelmingly English. And when you have people publishing, people still publish in journals, but they publish in Chinese and in English. So there's always an English version of the article that they produce because they want to be cited and read. And that was also true in the 19th century. It's just you would publish in German and French and English, the same piece, so different people would read it. It's just now English is always the reserve language. It's a great question.
I'm a physicist, so I'll just say as an aside, I graduated in 1979, and one of my pains was having to learn Russian so I could read articles, which was
You're one of the
useless.
last, actually.
One of the few C's I ever got in college. Yeah. This phenomenon of things being discovered by different people, often far separated in different places, recurs throughout science. Yeah. And I've heard it described actually that it's a completely post facto effect, is that we look back and we think we see this. But maybe, I know this is a little far afield from what we've talked about tonight, but the best example I know of would be Newton and Leibniz, who really had, as I understand it, essentially no contact. Can you talk a little bit to that?
Well, they had essentially no, it's kind of complicated. We thought they had no contact. It turns out that Leibniz actually had a copy of a manuscript by Newton and annotated it, and now we know that. But nonetheless, he did a different system. If you look at Newton's calculus and Leibniz's calculus, we can't do Newton's calculus anymore. If anybody remembers ever doing x dot and x double dot, that's Newton's notation. It's terrible. The ddx thing, that's Leibniz. So they're very different kinds of systems, and they wanted to do different kinds of things with it. But that kind of phenomenon where people could discover the same thing at the same time, some of it's post facto, where we look back and we see things that look similar and say they're the same. But some of it's very real, because people know what the cutting edge questions are, so they're all working on it, and whoever gets there first wins. So we have a system of credit that rewards firstness. It doesn't necessarily reward bestness. It rewards who gets there first. And that's a very important feature of science today, this credit system. So with Leibniz and Newton, we don't focus as much on, we want to know who did it first, we want to know who did which part of it first, but we don't focus so much on what they thought they were doing, and that's something I think we should pay more attention to. But there's plenty of other examples of this kind of thing, and for Leibniz and Newton, we don't have a publication, because they didn't publish their stuff. They had letters, and they told people. Now the standard is publish. Who publishes first wins. Interestingly, so Leibniz thought he didn't get enough credit for calculus, so he thought he should get more credit. He also wanted a job in England because his boss became the King of England, so he wanted to move to England from Hanover. So he asked for an adjudication of who got the calculus first. And he asked the Royal Society of London to decide it first. The president of the Royal Society of London is Isaac Newton. So I don't know what you guys know about Newton, but Newton was not a nice man. So it was no take no prisoners. Very Leibniz didn't get the credit. Is the short version of that. But so this anxiety goes back a long way. There's lots of elements of this. You even see elements. You start to see elements of it very strongly in the period that we call the scientific revolution. This kind of Copernicus to Newton zone. But it is your example is one of the classics. This is another classic one that's even weirder because there are 6 of them. It's just a proliferation, and that's quite common. There are like at least 3 to 4 people who are pretty close to the structure of DNA in 1953. And we only give credit to 2 of them. And we give the 3rd guy a Nobel Prize, and the woman died, and so she couldn't get a Nobel Prize. So but Linus Pauling gets no credit. This system is very interesting in its structure, but thank you for the question.
The periodic table has always appeared to me to be upside down because the actinides decay to more stable elements below, above on the table, and we're still looking for hydrogen atom nucleus to decay. So has anyone thought of correcting that?
Oh, people have done everything you can imagine has been done with the table. It's been oriented upside down. There are cases, and I kind of like this one. So these 2 series belong here. They're the lanthanides and actinides. They belong right here. Some people have 3D systems where this thing is tilted out of the board. So that way they all belong where they belong. People separate it by quantum shells, whether it's like they separate them out by SPD orbitals. People have done everything. People have inverted it. People sometimes reproduce hydrogen over there and hydrogen all the way over here by the halogens, because it's basically both. So yeah, people have done the inversion of the system. But this is the one that catches on. This is the one that fits on a wall. And that's not trivial, right? The 3D one doesn't fit on a wall. No one wants to use that. So there's lots of reasons why this gets stabilized, but by 1930, this is stable. Mendeleev never uses this system. He doesn't believe you should have this valley in the middle. So he thinks there should be a seamless across. So he intercalates these 3 periods here, half periods here of the transition metals, in between the other ones. And you get other patterns when you do that, more chemical patterns. This one is designed the way it is because of quantum theory. We believe that this reveals certain things about quantum theory.
In terms of what you said about Mendeleev getting credit today, it sounds like that is really related to the predicting elements.
Absolutely.
So had there not been the whole priority dispute, and if he'd published in German originally, do you think that would still be the case, that Mendeleev would get credit?
You mean if he'd published in German and not made the predictions, or?
No, if he'd published in German and made the predictions, but hadn't had this whole sort of very caustic, back and forth.
Would he still get the credit today? These are counterfactuals. I have to be officially opposed to them because they didn't happen. So it's not in the past. It's a guess about the past. But I'll play along and answer what he would have definitely gotten some credit. Because at the time, when the debate is happening, people would have still wanted credit for it, and whether or not Meyer wanted to start a fight, Meyer seems, from his correspondence, to be a reasonably peace-loving, easygoing guy. Other people would have claimed credit for Meyer for the sake of Germans. And other people would have claimed credit, as they did, for the sake of France. They claimed that Beguier de Chamcourtois did that. So other people would have made it nasty, but I think if there hadn't been a translation mistake and he published it normally, he would get credit. Whether he would share it or not share it depends on a lot of things, in particular how much we value prediction. And as chemistry becomes more and more like physics, not a separate science, but part of a joint physical science, that the standard of credibility, the standard of validity changes. And I think that change is what gives him the credit. So it would have happened even if there hadn't been the fight, probably, because that transition was happening due to a variety of transformations. But again, I officially can't guess.
Oh, being a history major, I need to inject something else. Since Germany really wasn't a country until 1870,
Yeah.
There might have been a fear to predict between 1860 and 1870 exactly what was going on, where Russia at the time was going through a vast eastern expansion, conquering various native people, similar to another country going westward.
Yes,
so
there's a lot of analogies
could
there.
That have had an impact?
They both have slavery issues in exactly the early 1860s.
Could that have had an impact, you think, on their thinking?
The Russian expansion or the German lack of unity? I don't think so. It's an interesting thought, but I don't think so because I don't think I can speak more about Mendeleev because we have more documents for him. In this period of time, he's pretty detached from imperial politics. He's very interested in what's happening locally in St. Petersburg. And there's a lot of uncertainty in St. Petersburg, too, if you push this way, because there's an attempted assassination on the Tsar in 1866. It almost works. It does work in 1881. Alexander II is assassinated. So there's a lot of uncertainty in the 1860s as well. Mendeleev starts out with a job at St. Petersburg University, and then there's a student rebellion, and they shut the university down for a year and a half. That's in the early 1860s. So he experiences uncertainty as well. It doesn't look as certain as it does to us now. On the other hand, the Germans, while they aren't a country, there's a German chemical society before there's a Germany. Because Deutsche means something. Germanness has a cultural unity in a way that actually Russianness in this period does not. Russia's a multi-ethnic empire with an enormous diversity of peoples in it. And so later on, Russia becomes much more, especially in its later Soviet incarnations and today, much more ethnically conscious than it is in the mid-19th century. But it's a very interesting thing to think about because this stuff does pop up. That is why those elements are named after countries. They're named after countries to declare something about their position, that Germany as a place it should have an element after itself. Russia has an element too. Russia is ruthenium, which is, there's ruthenium right there, element 44, because that comes from the Latin word for Russia. But that was discovered by a German-speaking person working in St. Petersburg in the early 19th century. I want to say 1830s, but I can't be specific about that. But that's part of declaring Russia a scientific country that matters too. So there's politics all over this, but I don't know if I would be so deliberate about putting those linkages together. Okay.
Back here, Dr. Gordon, and due to the time, this will have to be the last question.
Hello, thank you. I enjoyed your talk. In your answer to the physicist in the back, you mentioned that everybody knows what the questions are, what the pertinent questions are in science. And it's easy to understand today how that would be because there's an increased flow of information, people can communicate, and we know where the money is. But at that time, how did people know what the pertinent questions were and what was at the cutting edge?
So people, when you first said that, I was like, did I say that? No, now I know what you mean. Yes, I did say that, and I mean that. People knew that because there were certain topics that they knew were burning. This was not one of them when it first came out. The periodic system is a byproduct of writing a textbook. But certain questions, like what the structure of benzene is, benzene was problematic. People just didn't know what to do with it. And so in journal articles, and it's of a much longer time frame, but people do read the German or the French or the English journal articles. And so over the course of a decade, there's an obsession with benzene. People just know this is a problem. And that attracts people's attention, but it's much slower. The issue of the transformation of species, people have been gnawing at that particular bone for decades. Darwin had been gnawing at it for decades before publishing. I mean, like, everybody had been worried about that. He was worried about it in the 1840s. It didn't publish until 1859. 1858, 59, depending how you count. And there was a priority dispute there as well. But there are certain topics that kind of stand out, but other ones, like how heredity works, that wasn't a burning question. Mendel publishes on it and no one cares because it's not a burning issue. But some issues stand out. And the issue of how to calculate a law of gravitation from the trajectories of planets, that's a question, that's called the inverse problem. People are very, very worried about that particular problem. They know that if you have a central force, you will get elliptical things, but they want to know if you have elliptical things, do you get a central force? People are working on that extensively. To solve it, you need to invent calculus. So there's a push towards certain kinds of questions. But by no means is there unanimity, and there isn't unanimity today. There are some questions that we think are really crucial. And then there are some people who think it would be really interesting to know what caused ulcers. Not an important question. That guy got no funding, and no one cared about it. And then he got a Nobel Prize because it's pretty amazing. But he had to experiment on himself because nobody would actually give him any funding. So some questions people will still work on anyway, but other questions are really pushed at by the mechanism and the nature of the time. But it's a great question. It's much slower, but I think still a very recognizable process.
Thank you, Dr. Gordon.
Thank you all very much.
And thank you for attending tonight's lecture. Remember, next week, next Tuesday, we have a wait list for the first Nobel laureate lecture with Carrie Mullis. But next Thursday, the 21st, Nuclear Safety, America's Approach. There are still tickets available. Please go online at lindahall.org. Thank you and good night.